Fasten your seatbelts, kiddies, because we've got quite a bit to cover today. Yesterday we did vertical asymptotes, and today we're going to do both horizontal and oblique asymptotes. What are they? Well, let me explain. This is section 4.52, rational functions, our second day. So yesterday we did vertical asymptotes, and today we're going to do horizontal asymptotes. This is what they look like. You've seen them before on graphs, we haven't talked about them yet. This is that's what they would visually look like. And the big idea is that horizontal asymptotes are determined by the leading terms of the numerator and the denominator. So, for example, here, the leading term, there's only a couple of terms here. Here, the leading term is 1, and the leading term is x in the numerator and denominator. So you basically just focus on 1 and x, and you say that as x approaches infinity, or negative infinity, this will just go to 0. 1 over x will go to 0. You don't have to worry about the minus 3 because at the end of the day, when you're talking about these giant astronomical numbers, the minus 3 doesn't really matter that much. When the input value is 100, the output variable is going to be 0.0103. And as you get larger and larger, this number just gets closer and closer to 0. And as you approach infinity, the value of the function approaches 0. Same thing from the other side. If you plug in these increasingly more and more negative numbers, you get something increasingly closer and closer to 0. As x approaches negative infinity, the function will also approach 0. And that's how we know we've got a horizontal asymptote at 0. You can see y equals 0 here, and then you've got the dotted line, and there it is. The graph approaches it from the positive side and from the negative side, as x approaches negative infinity and positive infinity. Your horizontal asymptote is y equals 0. So you have to ask yourself, what's the degree of the numerator and what's the degree of the denominator? If they are equal to each other, like this, then you can just say, wait a minute, I don't need these terms. These terms are going to be kind of inconsequential. So if you have like an x value of 1,000,000, 1,000,000 squared is a huge number compared to just 2 million, and 1,000,000 squared is a huge number compared to these. These numbers won't really matter as x approaches infinity. These terms will. So you focus on these terms, 3x squared, 2x squared. You simplify that, you get 3 halves. You're going to have a horizontal asymptote where y equals 3 halves. You can even do the dotted line, and then you can see, although it might cross from the bottom up and then level out, eventually it'll approach the asymptote. Here, it approaches the asymptote from the bottom side. As x approaches infinity, the graph approaches 3 halves. Here, is there a horizontal asymptote somewhere? Well, you have to examine the leading terms. Since this is x to the fourth, they'll cancel out. You just have y equals negative 7 over 11. And here I've graphed it. Here's what Desmos would look like if you really stretch things out. I've graphed the line y equals negative 7 over 11 as a dotted line, and you can see that the blue function approaches it on either side. Eventually, as you get positive or negative enough, you'll get as close as you want to the line y equals negative 7/11. Here's a horizontal asymptote. You can see if you want to find the horizontal asymptote, you have to take the leading terms, and 2x over x cubed, well, that simplifies down to 2 over x squared, and as x approaches positive or negative infinity, this will just go to 0, so y equals 0. I don't have a graph for that, but you can graph it and you'd see, same thing. Let's say you need to produce the graph. Well, very important things to note are what the vertical and horizontal asymptotes are. To get the vertical asymptote, you remember from yesterday's notes that you have to set the denominator equal to 0 and solve, and you get here, in this case, x equals 0. Examine the leading terms to find the horizontal asymptotes, and you get 2x squared over x squared. These cancel out, and you get y equals 2. And then if you need to, you can take some more test points. If you don't have Desmos and you're just trying to graph this thing, what you really can do first is plot the asymptotes. The asymptotes are going to help you frame where the graph is going to go. So I've plotted the vertical asymptote and the horizontal asymptotes, and you know that the graph is going to be kind of nestled in among there somewhere. You don't necessarily know just from the asymptotes that these are both going to be positive. What you can do is you can take some test points from a table. And then if you plug in these x values, I've chosen these x values because they're very close to the asymptote and they're also far away from the asymptote. You can see we get these really huge numbers very close to the asymptote. All of a sudden you have to graph a number like 102. That's like way up here. So that looks like it's going up to the asymptote. It's approaching positive infinity from either side of the asymptote. That's kind of key to understand. And so then you take numbers that are far away from the asymptote and you get these numbers that are incredibly close to y equals 2. We know we have a horizontal asymptote at y equals 2, and they approach it from the positive side. Okay, so next, oblique asymptotes here. They occur when the degree of the numerator is equal to 1 plus the degree of the denominator. So the numerator is 1 more. For example, here, the degree is 2 and the denominator is 1. 2 over 1. The degrees are 2 over 1. The degrees are 3 over 2. They look visually like these diagonal lines. Oblique can kind of mean diagonal. And so here I've highlighted in blue the oblique asymptotes. They're not vertical, they're diagonal. And where's another one? Here's another one right here, oblique asymptote. How do you figure out when there's oblique asymptote? When the degree is the numerator is equal to 1 plus the degree of the denominator. And then you can also say here, how do you find the oblique asymptotes? Let me show you. So example 7 just asks, what are the asymptotes of this function? You know you're going to have some vertical asymptotes whenever the denominator is equal to 0. And it looks like we're going to have an oblique asymptote because the degree of the numerator is 2 and the degree of the denominator is 1. 2 is 1 higher than 1. So what we do is we actually divide. We're going to convert the function from this format into this format. And we do that by dividing the polynomials. We take the numerator and divide it by the denominator. So here's the numerator and the denominator, and we divide using polynomial division. We get 2x plus 1 with a remainder of 1. That remainder of 1 we can just rewrite here as 1 and then x minus 2 down here. So actually these two versions of the functions are 100% equal to each other. They're equivalent functions. However, we can see that as x approaches positive infinity and x approaches negative infinity, this term doesn't really matter all that much. The oblique asymptote is going to be just the function without the fraction over here, 2x plus 1. We have an oblique asymptote at y equals 2x plus 1. So we've got these two, the vertical asymptote and the oblique asymptote, and that's the answer to the question, where are the asymptotes? And if you want to know where they are, what they look like, then this is what they look like on the graph. Oblique at y equals 2x plus 1, and vertical at x equals 2. Although if they're asking for asymptotes, you don't necessarily need to produce a graph. You just need to produce the asymptotes. Number 59, this is copied out of the exercise section. Number 59, you might have to do something like this. They might ask for the graph. Well, a great thing to do first with a graph is to figure out what the asymptotes are. Here, this function is going to have a vertical asymptote when the denominator is equal to 0. That's when x is equal to negative 1, vertical asymptote. You'll see it in red below. Then it looks like it's going to have an oblique asymptote because you can see the degree is 2 and the degree is 1 here. So when we divide using polynomial division, we get f of x is equal to x minus, and this remainder here, we see the remainder is 10. So we put the 10 over what we're dividing by, x minus 10 over x plus 1. In this format, we can see that we'll have an oblique asymptote where y equals x. I'm getting that because of just ignoring this rational part, this fraction of the function, and just looking at this, x. The oblique asymptote is y equals x. Now, when you're graphing functions, it's always good to know what the x and y intercepts are. So you can set the whole thing equal to 0. When is this function going to equal 0? Well, when the numerator is equal to 0, and that's going to be x equals plus or minus 3. We've got the x-intercepts here, and there's 2 of them. You'll see they're plotted 3, 0 and negative 3, 0. They'll be in green below. And if you want to know what the y-intercept is, that's the easier one, actually, of the 2. You can just take 0, plug it into the function, and see what you get out. You get out negative 9. So you can plot the point 0, negative 9 as your y-intercept. And then if you needed to, you could take other test points, but this is what the graph looks like. Other test points might be something like negative 9, negative 9. Anyway, when you're asked to produce a graph without Desmos, without looking at the graphing calculator, then asymptotes are going to frame the whole thing. You can draw the asymptote first, and then the x-intercepts and the y-intercept, and any other test points you might care to choose. You can always check your work with Desmos. Next, let's say we need to graph something like this. This function, f of x is equal to 2x plus 3 over 3x squared plus 7x minus 6. Well, a very good first step is to figure out when are the vertical asymptotes. They are whenever the denominator is equal to 0. Factor it, and you get x equals 2 over 3 and x equals negative 3 when you solve. The vertical asymptotes below are going to be in red. What about the horizontal asymptotes? Well, for the horizontal asymptotes, you have to look at the leading terms. We know there's going to be a horizontal asymptote because the degree of the numerator is only 1 and the degree of the denominator is 2. So we know when we simplify these leading terms, it'll be 2 over 3x. And as x approaches positive and negative infinity, that's just going to go to 0. So it'll have a horizontal asymptote at y equals 0. The y-intercept and the x-intercepts, you can take f of 0. When you plug that in, you get 3 in the numerator and the negative 6 in the denominator. You get negative 1/2. So you get 0, negative 1/2 as a y-intercept. The x-intercepts would be when the whole function is equal to 0. And when is a fraction equal to 0? Well, when the denominator goes away and just the numerator is equal to 0. Solving that, you get negative 3/2 for an x-intercept of negative 3/2, 0. So now that you have the asymptotes and the intercepts, you get a pretty good picture. This is what the graph looks like. We know exactly where the y-intercept, the x-intercept is, the vertical asymptotes, and the horizontal asymptotes. And if you really needed to, if you didn't have a graphing calculator to figure out where things were, then you could take test points all along here and along here to figure out where the curve is. That's a lot of test pointing, but that's what the graph looks like. Example 9 asks you to graph something like this. Again, ask yourself where are the vertical asymptotes. It's where the denominator equals 0. When you factor it and solve, you get x equals negative 3 and positive 2. Again, you'll see those in the graph below. What about any horizontal asymptotes? We know there's going to be a horizontal asymptote because the degrees of the numerator and denominator are the same. When you simplify these fraction, you get y equals 1. The y-intercept, plug in 0, you get out 1/6. The x-intercept, solve for 0. When is the whole function going to equal 0? When the numerator equals 0, which is when x is equal to plus or minus 1. You can see this is what the graph looks like. We've got x-intercepts here in yellow, the y-intercept in green, the horizontal asymptote in blue, and the vertical asymptotes in red. Always good to check your work with a graphing calculator if you are allowed. here's a graph. First thing I notice is that the degree is 3 here and 2 here, so we're going to have an oblique asymptote. Are we going to have any vertical asymptotes? Well, that's whenever the denominator is equal to 0, which actually will never happen with the real numbers. No real number squared is equal to -1. So there's no real vertical asymptotes. The oblique asymptote you can get by doing polynomial division. So you take the numerator and divide it by the denominator, and you can see here you get 2x first, and then with a remainder of -2x. That's fine. You can just put the remainder over the over what you're dividing by, and you get this. So the function is exactly equal to y equal f of x of 2x minus 2x over x squared plus 1. For the oblique asymptote, you forget the remainder, and you just look at over here, you get y equals 2x. For the y-intercept and the x-intercept, you note that f of 0 equals 0, so it's just going to travel through the origin. And this is what it looks like. You can take more test points if you need to, but graphing it produces this, and you can make sure that you have the oblique asymptote and the intercepts. Last example, we've got a graph. I'm noticing here that the degree is 1 and the degree down here is 2, so we're going to have an oblique asymptote. And as I factor this, notice that we've got x minus 2 and x minus 2 over here. They're actually going to cancel out. And when they cancel out, you're left with 1 in the numerator and x plus 1 in the denominator. When things like this cancel out in the fraction, you have what's called a hole. The hole is going to be wherever this expression is equal to 0. That's where x is. So you can't have x minus 2 equal to 0, or else you're going to get a 0 in the denominator. This hole occurs because you're canceling this out. And this g of x, this function here is exactly equal to this function here, except when x minus 2 is equal to 0. So it's okay to say that this is the function just so long as you make sure that x is not equal to 2, because that's where the hole is. Let me show you what that hole looks like visually. Fast forward to the end. You can see this complicated function is the same thing as 1 over x minus 1, except here you have the hole where x is equal to 2. So from now on, let's just, instead of analyzing this crazy function, let's analyze this little function here, knowing that there's going to be a hole at x equals 2. Here you can see, if you're going to ask yourself what are the vertical asymptotes, it's wherever the denominator is equal to 0. That's an x equals -1. Ask yourself, when is this function going to have a horizontal asymptote? That's where the leading terms, 1 over x, that's as x approaches infinity and negative infinity. Why don't you tell me what they are? Pause the video and write it down, and then when you're ready, we'll move on. What is the y-intercept? It's when x is equal to 0. You plug that into the function, you get 1 over 1 is equal to 1, and that's your y-intercept. The x-intercept, you have to ask yourself, when is this whole function equal to 0? Well, whenever the numerator is equal to 0, which is never going to happen, so there's no x-intercept, as you can see right here. Those are the notes. That's a lot of them. I want you to start 42, copy the problem list, and do the first problem, and I'll see you in class.